Hi, I'm Nick. This is an analysis that I worked on in some of my previous work, and I thought it was interesting, and so I wanted to share it here. So first, I need to give you a little bit of background, and the little man you see over on the left there is about as much anatomical background as you're going to need. But basically, your intestines are full of bacteria, and things that are in your gut, including bacterial stuff, access your liver directly through a venous system called the portal venous system or the portal vein. And so, like I said, that blood directly drains stuff from your gut to your liver, and then the liver can go on to affect the brain in several different ways that I'm just leaving unspecified here. So now I need to get into a few more particulars. The first thing to know is that there is a substance called lipopolysaccharide, or LPS, and some people know this by the word endotoxin, but it is a bacterial product, and when it is injected into general circulation, it promotes sleep in animals. And LPS is rapidly cleared by the liver, and specifically by macrophages, but that's not really important here. All that's important is that it gets cleared by the liver very, very quickly. And then one more piece to this little part is that how LPS is affecting sleep is not really known. It's not known where it's working on. Now, the gut microbiome is comprised of bacteria, and these bacteria produce all sorts of things, including LPS. And like I already said, the liver is receiving blood from the gut, and importantly, this blood contains LPS, and so the liver is handling LPS that is coming right out of the gut from these gut bacteria. Now, I already mentioned that LPS causes sleep or increases sleep when it's injected into animals, and a general dose here that will affect sleep, or non-REM sleep specifically, is about 200 micrograms per kilogram. But doses as low as 1 microgram per kilogram can cause similar increases in sleep, just as robust, when they are injected directly into the liver via the portal vein. And importantly, I guess maybe it even goes without saying, but this low of a dose when injected into general circulation does not have these effects. In fact, maybe no measurable effects in anything that we did, at least. Okay. So the central hypothesis was that LPS from gut bacteria can affect sleep by acting on the liver. And this central hypothesis would be greatly supported, though not necessarily refuted or proved. But if LPS that was injected directly to the liver via the portal vein did not escape into systemic circulation, right? Because if it gets into systemic circulation, it starts to open up other potential sites of action outside of the liver. So the experimental hypothesis was that LPS directly injected into the liver via the portal vein would not increase systemic circulation of LPS. And so to test this, the experimental approach was pretty simple. So on day one, animals were injected. We used rats. They were injected into their portal vein with vehicle, just saline. And then blood was drawn at various time points thereafter, 5 minutes, 15 minutes, and 2 hours. And of course, that blood was assayed for LPS concentration. And then on another day, the exact same thing was done, but this time we used LPS instead of saline, blood drawn, and that blood assayed for LPS concentration. So now I want to get into the analysis. So I first want to comment on what would be what I would think would be an inappropriate way of doing this, but which would be very common, at least in the kind of the scientific community of which I was a part of, and that is to test each one of these time points with individual hypothesis tests. Okay, and this is inappropriate for a lot of different reasons. So one of them is obviously that these time points are not independent. Okay. So obviously time point 5 is related to time point 15 is related to time point 120. And so hypothesis tests are not really appropriate here. But another one, and this one I'm going to have to spend a little bit of time on, is that is that measuring LPS concentrations is not really what we want. We want the total amount to escape the liver, right? But these LPS levels, these measurements that we're making are only snapshots of LPS concentration. And I feel like that's a little bit that's a little bit unclear, and so I need to expand on that point. So here's our general, or kind of a generic circulatory system here. The portal blood, again coming off of the gut, is accessing the liver, and the liver, of course, pours blood back out into general circulation, and then that blood goes on to mix with other unspecified organs, and so on and so forth. And the first thing to appreciate about all of this is that LPS concentration is, of course, dynamic. It's always changing, right? And it's changing because LPS concentration is a function of influx, right? The total amount that is coming into general circulation from the liver minus the efflux. And then, of course, all of that gets normalized to the blood volume of the animal. That's just kind of a nuisance term here. I'll ignore it here soon enough. So every time that we are looking at LPS concentration, what we're actually looking at is two different processes. Or we're looking at the sum of two different processes here, or the difference, I guess. And the reason that this is important is because any LPS that gets into general circulation could affect sleep from outside of the liver and therefore refute our hypothesis. Okay? And so what we really want to estimate is the total influx of general circulation, not concentration. Again, concentration is also factoring in the efflux, the clearance of LPS from general circulation. Okay. So how do we go about doing this? And this is kind of where the interesting parts of this come, or at least interesting for me. So if I was to think about what LPS concentration would look like over time, it might look something like this, just a little temporal bump. So as LPS, if it is getting out of the liver, as it would start to come out of the liver, it would do so at kind of in kind of a titrated dose, so to speak. Right, so LPS into the portal circulation, it's going to encounter friction inside of the liver and then slowly start to trickle out. And as it trickles out, other clearance mechanisms, efflux mechanisms, maybe as I might call them here, are also becoming initiated. And so what we would get is just this little temporal bump, and that's it. So this type of a little temporal bump can be modeled with the equation that you see in green down there. Okay, and so that means that our LPS concentration also equals that formula down there. Okay, and actually LPS is always circulating in the blood at some kind of basal level, so there's an additional kind of additive intercept term here, or constant term that is part of this. So now, like I said, this temporal bump is a function of two different processes, the influx and the efflux. Okay? And it turns out, again, what we want to estimate is the influx, and it turns out that we can estimate the influx from this formula right here. Okay? There's no use trying to memorize it, but I do think that it's important that I kind of show you where that formula comes from. Okay, so here I'm just replicating the formula that you saw previously for LPS concentration, and the first thing that I'm going to do is just get rid of that pesky volume term here. So I multiply volume through. Now the stuff on the far right in the green, it should all be multiplied by volume, but we can just say that all of the terms on the right-hand side there, on the far right-hand side there, are just slightly different terms, no longer corresponding to LPS concentration, but just the total amount of LPS that's in the body, and that's fine. So I'm dropping the volume term. So I'm not going to go through every little detail of the math here, but basically, if we take the derivative of LPS, we get that the derivative of the green stuff is the derivative of influx minus the derivative of efflux. Now, when I take the derivative of the far right there, I get the term that you see here. And those terms correspond to the derivative of influx and the derivative of efflux. Okay? And so then that means that the derivative of influx is what you see here. And now if I take the integral, the definite integral of the derivative of influx from time 0 to time t, I get the term that you saw on the previous page corresponding to total influx. Okay. So coming all the way back here to the analysis approach, our first step is to fit LPS concentration, okay, in the two conditions. And before going on to what the second step is, I want to address this little bump here in the saline condition. So to read this, it would look as though when we push saline into the animal, into the portal vein, that we're expecting an increase in LPS. And so there's a few things to say about this. The first thing to say about this is that really the thing that we're after is the difference between the green curve and the blue curve. And so, so this little bump here is not really a problem when we want to, for the thing that we're after, which again is the difference between the green and the blue bumps or curves. The second thing to say is that the machinery that we're going to use to try to estimate these curves should be able to estimate the beta terms, the coefficients, to make this line pretty flat. But then the third thing to say is that it's not, that there might actually be a bump here in LPS concentration. So this LPS is actually ubiquitous. It's everywhere. No matter how hard you try to get rid of it or avoid it, it's everywhere. It's in the needles that we use. It's in the cannulas of the animals that we pump the saline into. It's in the liver itself. And so it's not crazy to think that pushing some saline into the portal vein could have the effect of pushing some LPS into systemic circulation. Okay, but anyway, step 2 then is to use the math that you saw in the previous slide to estimate influx from the LPS concentration data. Okay, so here I am just showing you the code for all of this, and of course I'm not going to step through every line of this code, but I will highlight a few important features. So the first thing is that, again, we're modeling LPS concentration. And LPS concentration cannot be negative, right? You can't have negative LPS in your blood. It's always a positive continuous value. Okay, and so LPS concentration is being modeled with a gamma random variable. Next is kind of the actual meat of the model. Okay, so this is that additive basal level of LPS that should just always be circulating. And here we're just using a random effects model that's accounting for the particular animal and the assay that we're using. Okay? And then here is the dynamic portion of the model. Okay, so you can look at the code and look at the formula and see how they kind of correspond. I'm going to come back to that in just a second. There's something to say. The next chunk is just the priors. This is well, these are just things that you need in order to make a Bayesian model run. There's a lot to say about priors, but I won't say them here. And this last part are just technical stuff to make the model run. There's one thing I do want to highlight, though, in the technical stuff, which is if you go down to the constraints chunk there, you'll notice that there are constraints for the beta time and the beta time 2. And these refer to the beta terms that are in the dynamic portion of the model. And if you look at the dynamic portion of the model, you'll notice that that beta 1 needs to be positive, and the exponent, so beta 2, has to be negative. And that is not coded in that dynamic portion of the model. Instead, what I have done is I have set constraints to make sure that the model, when it's estimating, is only considering positive values for beta 1 and negative values for beta 2, thus making the exponent negative. Okay. Okay, so when we run all of that, this is what we get. And so I need to step through this. So these the big thick lines are the expectation across time for LPS concentration in the condition where animals received LPS, red, or saline, blue. And then you have these wispy lines here, and these represent credibility intervals of the mean. So if you're not familiar with the credibility intervals, kind of the 2-second spiel about them is They're kind of the Bayesian equivalent to confidence intervals in frequentist statistics. So anyway, so what we see here is that that the red and the blue lines do kind of pull away, but their credibility intervals are heavily overlapping. And so it's not really clear that much is happening, if anything. Okay, but we don't want LPS concentration, right? Because again, LPS concentration is a function of two processes, and we only want one of those processes. We only want influx. And so going back through the math that we've already went through, this is what total influx looks like, okay? Again, red is LPS, blue is saline condition. And now you see that there is some amount of separation across time with total influx of LPS, right? Now, that's one way of looking at it, but it's not the best way to look at it. What we really want is the contrasts, or a contrast, okay? So that's what's on the right here in purple. And so a contrast is take a random red line, subtract a random blue line, and do that 100 or 1,000 times. And then what you get is an estimate of the difference between the two conditions, okay? And here, you can tell that it's pretty convincing that, convincing insofar as you buy the model and think that the data is good. But it's pretty convincing that the LPS influx increases after injecting LPS into the liver. And now, just to close the book on all of this, what are the implications for the larger experiment, right? So we found that probably LPS is getting out of the liver. But notice the scale on the y-axis. This is in nanograms. And earlier I said that kind of a relevant dose is in the micrograms. And so we are orders of magnitude less than micrograms here, right? So maybe 2 nanograms are spilling out, but that pales in comparison compared to what is needed to have any kind of physiological response. Okay, so that's it. I hope it was a little bit interesting for you, and thank you.